All right, so here's part two of the lecture for this week. I'm going to talk a little bit about frameworks. I know throughout this course I've been chatting a lot about Epoch and this framework that I've been working on and developing. I again want to sort of encourage you all to use that to poke around at it, but it's definitely more of like a C++ hands-on, heavy dev, hacker kind of thing. If you're just trying to play around with machine learning and deep learning in general, it's probably better to just be in some of the popular frameworks that are currently out, such as TensorFlow, PyTorch, and we'll go through some of those today, and I'll even go through some example code to sort of explain what's going on and to how to do the stuff that I've been talking about. I've already posted a couple of some bits of example code throughout this course in like the previous lectures for an SVM and linear regression, and those were done with just NumPy, which I'll talk a little bit about as well in this lecture. But often what you want is not to build this from scratch, although it's a good exercise, and I encourage everyone to do it as much as possible to really understand fundamentally how these things work and how they fit together. More often you'll be using something like PyTorch that sort of does the training for you, gives you these components that already exist that support both CPU and GPU training. This is not going to be a very like robust explanation of, okay, how do I get it to run on the CPU or the GPU? I'm not going to talk. I will mention it in some of the code examples, but I encourage you, if this is something you all to really go on. Maybe I'll post this on the Slack, on the Discord, to do some of the PyTorch tutorials. I do actually talk about one of them explicitly here as well. So let's get to it. So in the context of machine learning, everybody's always talking about frameworks. And just like any development environment, you've got people that sort of have their favorites and people who say this sucks because the other thing sucks or whatever. I'm mostly going to talk about PyTorch in the context of this course. The reason PyTorch is nice is that it's much more suited for iteration and experimentation versus TensorFlow. This is not to say that it's better than TensorFlow. TensorFlow is also a very popular framework, and I would argue actually TensorFlow is better suited for production. There's also this new one called JAX, which I know nothing about, from Google, but it's funny because TensorFlow and JAX are both from Google, and PyTorch, I believe, is from Facebook. So if that's the game you want to play, I think JAX is maybe trying to sort of accomplish what PyTorch has done, but in the context of the Google camp. So I don't know. Do with it what you will. I'm going to leave politics out of it. But the big difference between PyTorch and TensorFlow is that PyTorch essentially runs your network every single time from scratch when you run it. You kind of explicitly say, hey, run my network forward, run my backward pass, optimize my network. You kind of explicitly do those things. And every time that the framework does that, it actually creates the network from scratch and builds it, runs it, and that kind of thing. Whereas TensorFlow is more of a compilation mindset where you define your network, it kind of compiles it into this format, and then you run it and both backwards and forwards and optimize it in the context of that sort of compiled format. And you might ask, well, what's the difference? Sounds like TensorFlow is more performant, and I would say, yes, I guess it is more performant. The problem with TensorFlow in the context of development and experimentation is that the compiled format isn't as flexible as the sort of on-the-spot type of approach, right? We haven't talked too much about it, right? But what if you have a conditional sort of flow? TensorFlow can do conditional networks, but it kind of unrolls them in a particular way. It has to sort of hard code the things that you do because it doesn't have that ability. While it is better for production because it can run things faster in this compiled form, because you're not paying that overhead every single time you're doing training or whatever, it is not able to sort of change the network on the fly as a result, right? So generally, I've come to a place where I'm using PyTorch for most of my work, and then for the more production stuff, would look at TensorFlow as an alternative. But I don't know. It depends what you're doing. If you're in a data science company, just trying to get these algorithms to run better and faster, you're probably using TensorFlow. If you're a researcher, you're developing some new idea, you're probably using PyTorch. But yeah, I've heard a lot of really good things about JAX, but I don't know much about it to really comment on it, so it's another thing for you all to look at. So let's talk a little bit about what these frameworks really do, and ultimately what you're really getting out of it is this concept of autograd, or an autogradient framework. As we talked about before, all these networks sort of take the form of this computational graph for us to analytically solve for the gradient of each stage of a network. Might be sort of annoying and very difficult, especially as we're changing it all the time. And so what we can do is instead encapsulate each one of these components in these modules that can be forward propagated and then backward propagated, and then propagate those gradients through. And what these frameworks do largely is give you an ability to create these graphs. They give you the components that then can determine what those gradients are, and so on and so forth. So in something like PyTorch, you could set up a computational graph such as this, for example, where you can see the loss, that's our loss function, and then we add all of these different things, and we can essentially kind of have these weights that have these gradients, and we can automatically determine what the value of the gradient of D respective to W4 is, and we can push that all the way through the network. So it just does this for us automatically. So yeah, that's all these frameworks do. One thing I think is important to mention here is this concept of this thing called Jupyter Notebooks. So you can these frameworks are largely Python frameworks, and you can obviously just write the code and run it in your terminal and use an IDE. That's fine. Some people do that. The Jupyter Notebook is nice because what it allows you to do is sort of visualize these things. What you'll often find is the amount of code that you write for machine learning isn't like a lot of code, but you're constantly tweaking things and playing with things and so on and so forth. And so Jupyter is a nice sort of way. It's just a Python package, by the way. So to launch a Jupyter Notebook on your computer, you download the Jupyter package, you run it, and then you can load up a browser localhost and use it in there. And it has access to your system, so anything that all the packages you've installed, it can even access your system path and so on. And very often you use Jupyter in the context of a virtual machine or a Docker instance or something like that, which we'll talk about. So Jupyter is a really nice thing. You have these ideas of code cells and text cells, and it's nice too because you can use it to sort of like do a project and a proposal or a project to write up. And a report and things like that, as well as just writing code and running it and creating algorithms. So very powerful. Another thing, so I mentioned you can run a Jupyter Notebook on your computer. You can do it in Anaconda, which sets up a virtual environment in your terminal. You can do it in a Docker container. You can set up there's like a million different ways to skin that cat. That might be really annoying, and keeping track of it. Also dealing with system administration and making sure that your terminal supports, let's say you're on like Windows with WSL2 and you have an AMD GPU, and like just a headache. Like all these things are really annoying to deal with, especially when you're just trying to write some code, right? And just get something on paper. Like just getting something to work, sometimes you just need something to get going. And so Google Colab is that thing. I can show you, for example, Google Colab here. Here's the example of our this code that I put up for you all. In Google Colab, you go to Google thing. One of the nice things is you can actually connect your Google Drive, which I don't have the code for here, but you can actually attach a Google Drive. You can have an easy way to sort of share files between your Google Drive and your Colab. You can run things like importing NumPy and so on and so forth. So it's a very convenient little thing. You can just pop open an instance. It's free. You can use both the GPU runtime or a CPU runtime. For example, I can where do I change my runtime type? See, I can go here and I can say I want a GPU or a TPU, right? And it's free. And I think you can pay to get faster GPUs and things like that. So it's a pretty flexible solution, and if you do your project in this, that's fine. That's great. This is a good. This is where I do a lot of my hacking if it's not in my terminal or something. But yeah, you can also do this there's a million different ways. At the end of the day, all this is doing is it's running a Jupyter Notebook in a virtual container somewhere with access to some amount of GPU acceleration with proper system infrastructure and support for that. So it just allows you to get to the meat of the problem without getting distracted with all these other things in the beginning. So I've used NumPy in some of the examples already, and it sort of probably requires just a little bit of a mention. NumPy is a Python package that allows you to do scientific computing with tensors. I believe it's a requirement, like a dependency of a lot of these frameworks. And often, like even in PyTorch, you have a function that specifically takes a tensor and converts it into a NumPy, and a lot of the functions take NumPy values as inputs. So very powerful, very easy to learn and use, and I highly recommend you all sort of check it out if you're going to be using PyTorch, something that's really good to learn a little bit about. So PyTorch is basically a Python adaptation of Torch. So in the early days of machine learning, there were things like Caffe and Torch, and these were like C++ frameworks, and then they got adapted with Python, and so PyTorch is the sort of Python adaptation of Torch, which again, I'm new enough to this field, I don't really know much about the history of that. But again, like PyTorch, what it does is it gives you an ability to set up these computational graphs, these networks as we've been discussing. It has many different components available that you don't have to really worry about how they work. So for example, on this right, this is actually taken from a tutorial from the PyTorch page. To use Torch to define a particular network, you would then override this class of module. In the initialization, you can see here what it's doing is it's setting up a bunch of different components for itself, like conv1, pool. You can see it again defining this convolutional layer, a max pool layer, again, another convolutional layer, and a bunch of like fully connected layers, right? These linear layers. The numbers you can look up on the documentation, but largely this says how many filters on the input, how many output filters, and what's the size of the kernel. You can also specify padding and stride, and because Python is a very kind of friendly language to verbosity and being able to be explicit, you can actually write this code in a very clear way, as you'll see in some of the later code examples. So now we've defined our network, so when we create this object, it'll just automatically, create these little components. These, as you can see, don't have any relationship to each other. They're just sort of there. But then we define within this module this forward function, and the forward function then tells this how to run it. So we're going to take our input x, and we're going to pass it through our first convolutional stage, and then a ReLU, right? And then we're going to run it through our pool. So this is basically convolutional ReLU pool. Then our next layer is going to be the convolutional 2 ReLU pool. And then we're going to do this thing called xView. And the reason we're doing this, by the way, is because the output of x at this stage is a convolutional volume, right? It's probably going to be something like 16 by, I don't know, whatever your input has convolved through these, right? Because whatever. And so we have to sort of reformat it into a different kind of format. The -1, by the way, just means it's a don't care, right? So it basically says one array dimension is going to be this size, and whatever's left, well, I just want you to chop it up. So there's sometimes these lines like do a lot more than they look like they're doing, but really what we're doing is we're just reformatting this, because keep in mind x may be a mini batch, right? So we may have a number of different x examples that we're running through this at once, and then now we have a fully connected layer running through a ReLU again and again, and we output without the ReLU because we're going to apply a softmax loss to this, as we'll see in a minute. And then, all right, here we define our loss function, so our criterion, the cross entropy loss, which we saw in the logistic regression problem, right? And the optimizer, as we discussed, we have this optimizer, stochastic gradient descent. We use the parameters of our network. So the net has a function called, a parameter called function. This is just from the NN module. And what this means is that to the optimizer, we're saying, hey, I want you to optimize the parameters of this network. So this is the way that we connect the optimizer to our network, our learning rate, and our momentum. So we can use momentum, for example, as we discussed in the previous lectures. And so this sort of sets up the loss function, and then it sets up the optimizer to be used in the context of training. And so now for every iteration, it just kind of comes down to, again, that anatomy of the problem, right? We do a forward pass, we evaluate the loss, we run the auto gradient, so we figure out what the gradients are, and then we apply the gradients. So you can see how convenient this is, right? So for every epoch, we do 2 epochs, and we do this for so PyTorch also had this idea of a data set loader, which I think is really, really powerful, because what it will do is it will just essentially like select these data sets for you and like mini batch and stochastically sample your data set. So that's worth kind of a read as well. But what I'm doing is, for the number of iterations in my data set loader and the data for each one of those mini batches, I'm going to then take the inputs and the labels. I'm then going to zero out the parameter gradients, because I want to start from my gradients, I want them to go to 0 before I calculate them. Now I'm going to run my inputs through my network, so it's a forward pass. Then I calculate the loss, right? The loss is just this function, the criterion, right? And I'm passing to it the outputs, which is my forward and my expected, right? So this is, the loss should be the loss between my outputs and my expected values. Now I have done the calculation of the loss. I can now run this loss backward function. This is where the entire auto gradient thing happens. And the way that this works is, you have to think about this, and the criterion gives me back this object. This object takes as an input the outputs and the labels. The outputs are this object that my network returned in the forward pass. So the forward pass, it's going to return this value x. This x is a tensor, so if you actually look at the tensor, it has all of the different, the computational graph attached to it. So now we can basically start from the loss and then back propagate through this computational graph that produced the loss to then determine the gradients at every stage. And then the optimizer.step, what it's doing is, now that we have the gradients, because keep in mind we have these parameters, when we created the optimizer, we have the parameters, and so that's passing to our thing. Those parameters have a gradient now associated with them, because we've gone through the entire thing. Now we step one step of the optimizer, which applies our learning rate and our momentum or whatever else we want to do. And here, this is just a sort of some metrics about our training process. So this allows us to kind of see what's going on. So it's a lot to kind of get in here, but really it comes down to 4 things. You define your network and your loss function. Then you forward pass your network. Then you evaluate the loss. Now you run the gradient on that loss. And now that you have the gradients, you apply the gradients. So it's actually pretty straightforward. It's almost like a game loop, right? You have to do all these things, and then you do it again until you eventually get to either per a set of iterations, or maybe you have some other heuristic that you wanted to use to determine when to stop, or when to, or how to deal with that. I have one more example. I'm not going to go too deep into this. This is a little bit more of a sophisticated example. You can kind of see how training a model could be approached in a little bit more of a systematic way. So in this case, we have a function called train model. We start off with a model optimizer, so we've defined the optimizer somewhere else. And you can kind of see it's kind of the same idea. We go through all of the x's in the training, in the data. We want to do it in CUDA, so we're using it with a CUDA. We're converting it into a CUDA thing, which just moves it onto the GPU. And then we calculate the loss of the model against this value. So this is a little bit of a different approach, because this is actually not using any y values at all. We zero out the thing, we take the loss, the backwards of the loss, and then we optimize in step, and that's it. And so we just do this over and over again. If you had a y, you would just pass the y to the loss as well. So you don't actually have to worry too much about it, which is pretty cool. And then in this case, it's the same idea. You just evaluate the model loss. So this is for test, which means that you're testing the model against real data. And here you can see the training for a certain number of epochs. right? So I would call this with my model, and it would then call these other functions to then figure this out. And you can see the optimizer set up as Atom with the parameters of the model passed in, and so on and so forth. So this is just kind of a sort of more fleshed out version of what we saw previously, although this is an unsupervised example, meaning it doesn't have wide labels. And the model here is a little bit interesting, right? It looks exactly like what we just did, except here we're defining a loss function instead of using that criterion. So you can actually put this function inside of your module. So I'm initializing this. The dimensions is just this, and I'm setting up logits as being a parameter, a set of parameters that this model has. And as you can see here, requires grad is equal to true. So these are the parameters that I'm going to be using in my model. And then when I calculate the loss, I'm just applying this cross entropy against the logits and this input. And so what I'm trying to do is actually I'm comparing two distributions. So this is a slightly different approach, but kind of the same idea. So yeah, next we'll talk a little bit about recurrent neural networks, and as we've already touched about it a little bit, unsupervised learning, and we'll start off with clustering and like k-means clustering and dimensionality reduction. So cool. Happy PyTorching.